In the last part of the tutorial we looked at the function object in conjunction with the line object, so hopefully you understand how that works now. And now we've got a patch which looks to some extent quite similar, as indeed it is. So just as before, we have a noise tilde object which is producing a noisy sound, white noise. We have a function and line object up here. We have the send tilde and the receive tilde, both referring to the same data because they both have the same argument. So the sound goes through the gain object to the output. But we have a new object, which is this one, reson tilde, which we will look at in just a minute. But just as the exercises demand, we will go through these comment boxes and do what they ask. So in relation to the function object, we have these set domain messages that are being sent, and these control the duration of the envelope that the function object is outputting. So if you set it to 1000, it will give you an envelope of 1000 milliseconds. If you set it to set domain 2000, it will give you one of 2 seconds. And it asks you try making the envelope length 5 seconds, so we will simply unlock the patch, change this to 5000 milliseconds. When I click set domain, it will change the length. We don't actually see it, but if I hover over the last point in the function object, then we see that the x-axis now goes to 5000, whereas before it was only going up to 1000, I think, which is the default. So that is that part of the task done. Next bit, it says send the output of reson to a spectroscope object to see the spectrum. So we will make a spectroscope object. There it is. And if I connect the outlet of reson to that, what I haven't actually asked you to do is to trigger a sound, but you can do that by clicking on the button object as we've done before, and you will hear a sound of 5 seconds in length. And by the sound of it you can hear a definite pitch in there. So and that is because this object reson tilde is a resonant filter, so it is filtering the noise in a particular way, which is being controlled by the frequency input and the Q input, and the frequency input is at about 400 Hz, so that's why we get that slightly pitchy sound which is at 400 Hz. So you see that there is a slight peak in the amplitude of that part of the spectrum when I hit the button. And I can change the frequency of that node using this frequency input here. So I can change it to, say, I don't know, 2200 Hz. And we see that this, well we hear it first of all, but we also see that the high point of this spectral display has changed. So we can hear that the resonant filter is definitely working when we change the frequency. I also ask you to have a look at the sonogram view for the spectrogram object. To do that you can click on it, go to the inspector window and choose display mode sonogram. That changes it to a white display. When I lock the patch again and click on the button object, you'll see it as a sonogram output. We could also, in the inspector view, change the frequency axis to a linear scale, which will make it display the frequency more obviously as we hear it. Let's lock the patch again. So a moderately high sound appears on the graph as being quite high up in the display. Before it was quite low down. So we've explored that. Explore the frequency and cue controls for the Reson object. We've already explored the frequency input. By the way, I should point out that the Reson object, you might probably already work this out anyway, but the Reson object has these three inlets which control different parameters. The first inlet controls the gain, which you'll see if I hover over it. So as in the last part of the tutorial, we've got the envelope controlling the loudness. It's just that last time we were using a multiplication object to control the loudness. Now we're using the gain input for the Reson object. Basically it's doing the same thing though. We have an inlet for the frequency we've already been playing with, and then we have an inlet for cue, which is the bell curve, or the width of the bell curve of that filter. And we can make that bell curve narrower or wider in order to make the sound more or less pitchy. So if I reduce the cue down to say number 1 and click this, you'll hear we have something much more akin to the original noise-based sound, although you can still see that there's a bias in the 144 Hz range. Actually, I'm going to increase that a bit. Because I don't. There we go. But if I increase the cue to say 50 or more, then it becomes increasingly obviously pitched. And if we increase it to say 600, we get something ever closer to a kind of sine wave, because you're narrowing that window for frequencies to a very precise area of the spectrum. Notice also when that happens that we are, of course, because we're narrowing that window, we're also reducing the amount of energy that can come through, so that makes the sound that much quieter. So we've had a look at the frequency and the cue, and I realised that I haven't followed these comment boxes in order. Never mind. So it says change the envelopes in this object. Well, we've already tried that in the last part of the tutorial. So you click in the space to add a new breakpoint and thereby change the envelope shape, and you can shift click it to remove those nodules. One other thing we can do is to clear the points in the function object completely, and we'll do that by adding a clear message. Click on that and it gets rid of everything. I'll put an envelope back. So that's that. I suppose the only thing we haven't actually looked at is this load mess object, which I'm not going to talk about much now. It's basically a means of ensuring that the numbers 420 are sent to the frequency and cue number boxes when the patch loads. We'll look at load mess, which stands for load message, and load bang in due course when we talk about initializing your patches and making them more usable. Right, so we'll get rid of that. The frequency and cue values are static at the moment, but we might want them to change if we want a percussive sound that isn't necessarily static in terms of frequency or cue. And we can use the function object to do the same thing as we're using it to do for gain. So we'll do that. I'm going to get rid of these frequency and cue inputs altogether. So I'm going to get rid of those. And I'm going to copy across what I need of this lot, which is the function object and the line object. I don't really need this display here, but I'm copying it across anyway. So I'll connect that one to the frequency input, and I'll just make another one and connect it to the cue input, like that. Now I want them all to be triggered at the same time, so I don't want individual button objects for each one. I'm just going to use the same one as right at the top to control all three. And the same actually with the set domain message. I'll connect that to all three as well. So you saw this bit in the last tutorial. I'm just using set domain with a $1 wildcard and throughputting these various numbers. So that means that if I lock the patch, then I click on, say, 2000 for the set domain, then it changes all three of them so the envelopes of all three are going to be appropriate lengths, or at least they're going to be consistent or comparable with each other. Now, if I click this now, we don't hear anything. Why not? Because the frequency is set too low. If you notice when I click on the button, all three of these line objects are outputting values from 0 to 1 and then back to 0 again. Now that's fine for the volume control, and to some extent it could conceivably be alright for the cue as well. But for the frequency, we are asking it to filter at a frequency of 0 to 1 Hertz. Well, that's too low to hear anything. So we need to change the range of this function object, just as we did in the previous tutorial, in order to get an appropriate range. And there are two ways that we could do that. One is to use a scale object, which is what I propose in the exercise sheet. And to do that, all we do is to add a scale object here. And it requires a little bit of explanation, which is that scale takes 4 arguments. It takes the input range of values, and it takes the output range of values. So line will be outputting values between 0 and 1. So I'll put in 0, oops, actually sorry, I need a tilde on the end of that because we're dealing with signal. 0 to 1. So that's our input range that's coming out from line. But in fact, if we say, as I think I propose in the exercises, that we want to accommodate a useful frequency range, say between 500 and 5000 Hertz, then we can scale those values from 0 to 1 to those that wider range of values. So I just put in 500 to 5000. I've put in the decimal points through habit, because Macs can be a bit picky about whether you write in integers or floats when you're working in the control domain, so I just tend to put in the numbers as decimals irrespective. But anyway, this is our input range from 0 to 1, which is coming out of the line object, and is obviously determined by the function object, and mapping it to a range of between 500 and 5000 Hertz. And if I do that, connect those two up, then you should hear that we get at least some sound. And we can make a shape that's different from the one we've got for volume. And we should hopefully hear a difference according to the shape we've drawn. So we have an envelope that's controlling the volume, we have an envelope that's controlling the pitch. And we might want to do the same for Q, so that the Q changes over time as well. And I'm going to scale it from 0 to 50. So once again, my input range is 0 to 1, my output range is 0 to 50. And it might actually help if I copy down these signal number boxes so that you can see what's actually being output. I will change the shape in here, and you should hear that work. So at the beginning we have quite a noisy sound, which then becomes progressively more pitchy as the Q increases, or the bell curve narrows. And at the same time, of course, we've got this increasing frequency here. So that's one way of controlling the range of the output from line so that it is within values that are useful to frequency and Q. Another way of doing it is what I showed you in the last tutorial, which is to connect these up again, is to use the set range message into the function objects. And so in this case I could say, do exactly what I did before, which is to set range to 500 to 5000 for the frequency function object, and set the range from 0 to 50 for the Q. And remember, when I've locked the patch, I then need to press these buttons, because if I don't press them, then those messages don't go into these objects and nothing changes. And remember that I'm using this set range message to save me having to go into the inspector window and change the values for range, which if I did that, then we would scrunch up these shapes. So we should get exactly the same effect as we had before going through scale, but this time we've changed the range of these function objects to make them do the same thing. There you go, exactly the same result. Which of those two you choose to use is entirely up to you. If you prefer using scale, I think it's useful for you to know scale because you might use it for other things. But one advantage perhaps of using the set range method is that you will see from the X and Y labels in the function object what frequency you are working with. For example, in the frequency function object, you can see that Y is going down to 3000, and of course we're referring to hertz. So that can be quite useful just to know what you're working with in terms of the pitch. So that's our basic, potentially our basic drum synth. And of course, once you've done that, you can start shaping those sounds and perhaps make them a little bit more akin to real-world percussion sounds. I mean, they're never going to be precisely real-world percussion sounds, but closer than they are at the moment. So I think I asked you to make a snare sound, so let's try doing that. And the way to think about this is to think, well, how is a snare sound constructed? What is its gain envelope like, or amplitude envelope? And that, of course, is going to be a very, very sharp attack with a rapid decay. So we will institute that, or emulate it using our function object. What about its frequency? Well, you wouldn't have a glissando-like character to it in here. The ring is probably more complex than I can really emulate here, but I will give it a, I don't know, 2600 hertz kind of focus. And then the Q, well, you would definitely start with a noisy sound, because any kind of percussive sound starts with a fairly noisy sound, and then perhaps it would become a little bit more focused in terms of its kind of frequency content as the sound went on, but not necessarily dramatically. So I will, whoops, well, I'll have a fiddle and see. So if I lock the patch, oh, I don't need to, it's already locked. So we have a snare-like sound. Maybe it's a little too high pitched, so we can bring down the Y value in this function object, see whether that makes a difference. That seems a bit better. Never going to be exactly a snare, but you could probably make it slightly more snare-like than I have if you were to finesse it a little more. But you get the idea. And you can be quite extravagant with the kinds of sounds that you produce using this. So I could do a kind of wiggle in here. And one that maybe slows down in the speed of its wiggling. And we could do the same with pitch. And we could start with a noisy sound, but then have a kind of wiggle of Q as well. I don't know how much of that you'll notice, but we'll see. Okay. So we have a kind of a percussive attack, and then a bit of a frenzy, and then it kind of calms down a little bit. And of course, you know, you can change the length of the sound. Maybe we would want to make that attack a little bit shorter. And at the end of the sound maybe we'd have a little tail that kind of rises. That's alright. So you can fiddle.